Right. So, let us understand now the simplest aspects of the transitions of phase of a system between the gas and the liquid phase and the liquid and the solid phase. We need to be a little more precise when I say solid phase. Generally the phase that we have in mind is a phase where the liquid crystallizes into a regular array called a crystal. So, the crystalline solid phase is what we are interested in, not other exotic kinds of solid phases. So, a generic or typical diagram in the phase diagram, so to speak, which describes, which helps qualitatively to understand these changes of phase, is provided by what is called a phase diagram or a PT diagram here. And what it means is the following. So, if you plotted the temperature on the horizontal axis and the pressure on the vertical axis, remembering that every point on this plane, on this quadrant, since P and T are positive on this quadrant, any point like this is a thermodynamically stable state of the system, which the system under study, and we are going to, for simplicity, look at systems which have just one molecular species, single component, simple substances. Such a substance, every point on it would correspond to this temperature and that pressure is in a state of thermal equilibrium. The volume of the system is connected to P and T, once you tell me what P and T are, by the equation of state. So, there exists a relation, an equation of state connects P, V and T for a given amount of the substance, for a given n, the number of molecules in the system. So, we will assume that there exists such an equation of state, could be a very complicated one, much more so than the van der Waals equation of state, and every point on this plane is a thermodynamically stable system. Now, when you plot P versus T, the following is observed. It is observed generically, typically, that at low pressures and sufficiently high temperatures, the system is in a gas phase and remains so in this region. At a sufficiently low temperature, there comes a point where if the pressure is increased, for instance, the system liquefies, and this is the liquid phase of the system, with a slope which looks like this, separating the liquid phase and the crystalline solid phase. And there is a further curve which goes down here. Schematically it actually cuts here and then it becomes a solid at the lowest of temperatures, but schematically this is all that we are interested in at the moment, which separates the solid phase from the gas phase here. These curves are the curves on which two phases can coexist. So, this is called the liquid gas coexistence curve, liquid gas and what it does, it's got the following physical implication. It tells you at a given value of the pressure what the corresponding boiling point is. In other words, if you started at this point here in the liquid, kept the pressure the same and increased the temperature, as you cross that temperature the liquid boils into the gas. Similarly, if you started at the same pressure here and lowered the temperature, at this temperature it condenses into a liquid. So, this curve, the liquid gas coexistence curve, is also called, the curve which separates liquid from gas is also called the boiling curve. And right away let us remark that we know from elementary considerations that if you increase the pressure on a gas, the boiling point increases, and indeed it does. You go up this here, you are going up in pressure, the boiling point increases up here. The slope of this graph tells you how the boiling point increases, and if you recall, you have this thing called the Clausius-Clapeyron equation, which I will come back to a little later, which tells you what is the change in the boiling point for a given change in pressure. Here, what is the increase if the pressure increases, and so on. It is related to the slope of this curve, which we will see. So, the other name for it is a Boiling curve. Similarly, there exists a curve here which separates the liquid from the solid with a somewhat higher slope, much higher slope, and we will see what that means. This thing here, this curve does not have to be a straight line, this curve is the solid liquid coexistence curve, which you could also call the melting curve or freezing curve depending on how you approach it. So, if you start here at a fixed pressure and increase the temperature, you would melt at that particular temperature. Similarly, if you started in the liquid phase and you lowered the temperature, you would freeze into a crystalline solid. This substance would freeze at that particular temperature here. So, the solid liquid coexistence curve is also the melting or freezing curve. The liquid gas coexistence curve is also the boiling curve, and both these curves tell you how the corresponding transition point, the temperature, changes as a function of the pressure. This curve here separates the solid from the liquid gas phase directly. So, it means that the solid can directly evaporate into the gas, or the gas can directly get deposited as a solid if the conditions are right. And this curve here is a solid liquid, solid gas coexistence curve, is also called the sublimation curve because that is what is happening. If you recall, sublimation is the name given to the process by which a solid evaporates into the gas directly without going through the liquid phase. The three of them typically, generically meet at a particular point, and this point is called the triple point. Since I have said that every point on this plane is a point of thermodynamic equilibrium for the system in whatever phase it finds itself in, on these curves it finds itself in two different phases. So, the substance spontaneously separates into a liquid part and a gas part, and they coexist with each other, which is why it is called a coexistence curve, and you have two phases in coexistence on any of these curves here. But at this particular point, the solid, liquid and gas phase all coexist, and it is called a triple point here. Now, right away I should say, I am going to talk about this diagram in some detail. Right away I should say that one can ask, what sort of crystalline solid can one have? Well, it depends on the pressure and the temperature. It turns out that most substances would have several kinds of crystalline phases, several kinds of crystalline order, such as cubic kind of symmetry or triclinic symmetry or hexagonal symmetry. The crystal classes have been classified depending on their level of symmetry, and you can have, as you go up here, you can have, as the pressure increases, you can have closer and closer packed kinds of symmetry, like face centered cubic or body centered cubic goes into face centered cubic and so on. So, you can have many such things happening. So, you could have things going off like that. So, there is a coexistence of two different solid phases and so on. You can have various kinds of complications. But you could ask, how do I know that the triple point where three phases coexist is the only kind of point where you have multiple phases, more than two coexisting? Can we have four phases coexisting? Can we have a picture like this, for instance, with one kind of crystal here, another kind of crystal here and so on? And there is a rule in thermodynamics called the Gibbs phase rule, which says that for simple substances, single component substances, the maximum number of phases that you can have in coexistence anywhere in the PT plane is 3. You cannot have more than 3 phases, and that is why we stop with this with the triple point where the solid, liquid and gas meet, and this is called the Gibbs phase rule. For simple single component substances, one chemical species, one molecular species, you can have no more than 3 phases in coexistence at any point here, and this is one such example where you have 3 phases in coexistence. Moreover, one can ask, where does this curve end, where does it keep going? Well, this curve, as I said, generally comes and hits this very, very low pressures, and below that it remains a solid, so we will not get into that here, but this curve definitely ends at some finite point, specific finite point, and this is called the critical point. It is so important that I write it in capital letters. This was the critical point PC, Vc and Tc that I mentioned in connection with the van der Waals equation in the previous lecture. This is exactly the same critical point, and what it means is that there comes a temperature and a pressure beyond which you cannot distinguish between the liquid and the gas. This coexistence curve ends at a finite point. That is an important, very important statement. This critical point is a point where elementary thermodynamics fails for good reason. It fails, and you need much more sophisticated techniques to understand, using equilibrium statistical mechanics, to understand what happens at this critical point. In fact, the problem of this critical point is a general problem of critical phenomena. This problem was solved to satisfaction only in the 1970s or so. So as late as that. The point here is that as you go up this curve, remember that to go from a liquid to a gas at a fixed value of the pressure such as this, you have to supply certain latent heat of evaporation. So when you jump from this to this phase, the liquid phase to the gas phase, at this pressure, at this boiling point, you supply a certain amount of latent heat. But if you increase the pressure, you have to boil at a higher temperature, you supply a smaller amount of latent heat. And as you go up here, it turns out that there comes a stage, namely the critical point, where the latent heat required to go from the liquid to the gas phase tends to 0. So no difference occurs between the two phases, you do not see anything at all. On the other hand, you can also distinguish the liquid from the gas by the fact that the liquid has a surface tension. So there is a surface to the liquid, but as you go up this curve, the surface tension decreases, the meniscus slowly disappears, and at this point it is gone altogether. So you do not have any distinction between the liquid and the gas, it is some homogeneous fluid phase beyond that. Okay. That is a very crucial observation, because it also means that you could start here at some point in the gas phase, and you could, by a sequence of steps, all of them in thermal equilibrium, a sequence of states, move in this fashion and get to the liquid phase by going above the critical point and coming back by decreasing the pressure and temperature, such that without crossing any sudden transition point or boiling point or anything like that, you can go from the gas phase continuously to the liquid phase. So this is a very, very important observation. It says that beyond this critical point, the distinction between liquid and gas vanishes, and you can go continuously from the gas phase to the liquid phase by going around the critical point in the PT plane. Can we do the same thing here? Can we do the same thing for the PT, the coexistence curve between the melting curve between the solid and the liquid? Well, we cannot do so, because if you could do so, there existed a critical point here. It means you could go from the liquid phase, which has complete symmetry, it looks isotropic in all directions, it is completely the same properties in all directions. Such a liquid cannot get into a crystalline phase which has a lower symmetry than the liquid has. A liquid looks exactly the same in all directions, its properties are exactly statistically the same in all directions, whereas a crystal definitely is different in different directions. The atomic arrangements are different in different directions. Therefore, a crystal is anisotropic, a liquid is isotropic, and there is a breaking of symmetry as you go from here to there. And this means that you cannot continuously go from there to here, because you cannot continuously deform isotropic, completely symmetric, rotation invariant phase into a crystalline phase which has got a lower degree of symmetry. So The crystal has undoubtedly a greater degree of order, atomic order arrangement, but it has a lower degree of symmetry because it is not isotropic. On the other hand, a liquid is isotropic. So this is another lesson which goes contrary to what one might naively think, that the greater the symmetry, the lower the order. In fact, the gas phase is very, very symmetric in that fashion because gas is completely isotropic statistically in all directions. So again, the dictionary meaning of symmetry and order are actually quite different, although in daily usage one tends to use the two synonymously. It is not true, they are antonyms in some sense, and that is important to remember. So no critical point here, this goes on forever, or else it hits other phases. There are other there are branchings and so on, other curves, etc., and this could therefore have no end at all. No critical point exists here, but a critical point exists in the liquid gas coexistence curve. The sublimation curve pretty much behaves like the liquid gas curve. There is no critical point here because this comes and hits this origin here, and then it becomes a solid. So it hits a physical boundary, and therefore this does not display a critical point, but the liquid gas phase displays a critical point here. Now what we have been saying about the van der Waals gas is applicable. This point here is the coexistence region in the van der Waals isotherms. So if I plotted V here and P here and looked at this line out here, such a point as this for instance, this would correspond to the coexistence of a liquid and a gas, and that, remember, is given by an isotherm like this. So it means that if you brought the system to this pressure and temperature and therefore could compute the volume, you would have hit some point like this, which would then phase separate into a portion that is a gas and a portion that is a liquid by a well defined rule, and this single line here corresponds to that region there. In fact, this entire curve, every point on this corresponds to a region, this region on this PV diagram here. One has a similar VT diagram which I am not going to talk about here, but this suffices to understand certain basic issues here. So no critical point on this, there is a critical point on this. Just for reference, you could ask, when does this happen with water? This is a common substance, the most common substance we could think of. Well, the critical point is much higher than the normal boiling point at 1 atmospheric pressure, and that, as you know, is 100 Celsius or 373 Kelvin or whatever. But the critical point for water, Pc and Tc for water, this is of the order of 218 atmospheres. Remember, 1 atmosphere is 10 to the 5 pascals approximately, and Tc in this case is of the order of is about 647 Kelvin. 374 or something like that in Celsius. So it is very much higher, very, very much higher than the normal boiling point at 100 Celsius, and the pressure of course is not at 1 atmosphere but 218 atmospheres here. Okay. Again, for reference, in the case of water, one can ask where the, so here is a schematic for water. Triple point and then a slope which goes this way, that is a surprise for water. Of course we know this is true because what happens, PT here, what happens in the case of water is well known. If you press on it, if you press on ice, it melts. So it is clear that in this case the slope, the P versus T diagram, dP over dt, is actually negative here, out here. So this means if it were positive, it would say that this melting point increased with increased pressure, but now the melting point decreases with increasing pressure, which is why you can skate. The skate applies a pressure and it remains at the temperature is at 0 Celsius, it becomes a liquid phase at that stage and the skate slides. You need to lower the temperature further in order to solidify it. So that is what is reflected by the negative slope here, but the magnitude of the slope is still very high, but it is negative out here. Okay. The triple point, this triple point is approximately at it's at a very low pressure, and the temperature T triple point T is of the order of if I remember right 0098 Celsius. So it is just a little above the freezing 0 degrees, the freezing point at 1 atmosphere, but the pressure is much lower, is of the order of, if I remember right, it is about 600 pascals. So it is almost 0 Celsius, and the pressure of course is much lower than 1 atmosphere. It is at 600 pascals. Remember, 1 atmosphere is 10 to the 5 pascals, a little more than 10 to the 5 pascals. So low temperature, low whatever it is pressure, but the Tc is crucial. This thing has a dot here, critical point, and it has these, and the volume of course it depends on the amount of substance, but you can compute it from the equation of state of the system. Okay. By the way, water has a very complex phase diagram. As the pressure increases and the temperature is lowered, there are 14 or 15 different forms of ice. There is ice 1, ice 2 and so on. They have very exotic properties, and the full phase diagram of water is not known as far as I know, even because we could go up in pressure arbitrarily high and you could get all kinds of exotic phases. So we will not discuss that, but now I would like to turn to what is meant by the slope of this curve here, and that is the equation, the Clausius-Clapeyron equation. Now in elementary treatments you are used to the statement that the Clausius-Clapeyron equation gives you the rate of change of the boiling point with pressure or the freezing point of a substance with pressure, and it basically reads in the elementary way of writing it dP over dt on the coexistence curve, either solid liquid or the other coexistence curve, either the solid liquid or the liquid gas coexistence curve. This is written generally as the latent heat, corresponding latent heat divided by T times V2 minus V1, where T is the corresponding transition temperature, boiling or freezing temperature, and V2 and V1 are the specific volumes of the system in a given phase, in phase 1 and phase 2 across this. Now the problem I have with this equation is that you always have a confusion as to which is V2 and which is V1. It should be completely arbitrary, what you call 1 and what you call 2. I mean, whether I call this phase 1 and this 2 and this, or this 1 and that 2 should be irrelevant completely. In one case you have to supply latent heat, in the other case you got to remove latent heat. So I guess that fixes this, but this is not the right way to write this. The correct way to write this is the following. Remember that this latent heat is the amount of heat supplied or removed at the transition point. So it is like delta Q, where Q is the heat and T is the corresponding temperature, but we know that delta Q over T is the change in the entropy. So the right way to write this equation is to write it as delta S divided by delta V. Specific entropy, entropy per particle if you like, specific volume per unit mass or unit particle, whatever. So this of course you could write it as S2 minus S1 over V2 minus V1. You could also write this as V1 minus V2 in the denominator and S1 minus S2 in the numerator, and it would not change at all. Okay. So in the case of liquid gas, the slope, this here is the slope of the boiling curve is equal to, we are going from liquid to gas or gas to liquid, does not matter. So let us write this as S gas minus S liquid over V gas minus V liquid, where S is the entropy, and we know that entropy is a measure of disorder, and we know that the gas phase is much more disordered than the liquid phase. So this is much bigger than that, and the numerator is positive as I have written it here. The gas has a specific volume which is also much greater than the corresponding volume of same amount of liquid. In the case of water, for instance, we know that 1 cc of liquid of water gets into under normal conditions, boil at 1 atmosphere pressure, it becomes 1600 cc of gas or water vapor. So V gas is much greater than V liquid, S gas is much greater than S liquid. The numerator is large positive, the denominator is large positive. This is very large positive, this denominator here is very large, which means that the whole thing is the quantity itself is very small and positive. So this implies small positive slope, which is what we see. We see a small positive slope here. If you applied the same thing to the liquid gas, crystalline solid transition point, slope of the melting curve, then this would be S solid minus S, let us write this as S liquid minus S solid, so that it divided by V liquid minus V solid. Now we see there are two possibilities. The entropy of the liquid is always greater than that of the solid, no question about it. The liquid is far more disordered than the crystalline solid. So the numerator is large and positive, but the denominator can be positive or negative. There is nothing which says that the liquid could not be more dense than the corresponding solid, and the most notable example is water itself, which, as you know, at 0 Celsius ice has only 92% of the density of water, which is why it floats on it. So in that case V liquid is actually smaller than V solid and the slope is negative. So that is the reason why water had this very funny phase diagram where this actually went negative in this fashion. But for most substances they actually contract on freezing, and then V liquid is bigger than V solid and it is positive. So this will always be large magnitude but plus or minus, could be positive or negative, usually positive, but could be negative. There are substances which expand on freezing, like bismuth for instance, liquid bismuth will expand on freezing, or water itself does it. Now you could ask, why should it be large in magnitude? Well, this is certainly bigger than that, it is already a large number, but this quantity here is small because a liquid does not have a compressibility which is very much higher than that of the solid. The solid undoubtedly most cases will be even more incompressible than a liquid, but the change in density between a liquid and a solid is not very high. So the specific volumes are not very different. As we saw, it is about 8% in the case of water, it is small, and therefore the denominator is small of either sign, the numerator is large positive, and therefore the ratio is large in magnitude but could be of either sign. So that is the reason why in certain substances the slope goes the other way, but in usual substances it goes in this fashion here. And that is the genesis, that is the origin of the Clausius-Clapeyron equation here. Now one could ask, finally one could ask, what is it that is common between two phases? What is the quantity that does not change when you go from one phase to another? For this we need to go back a little bit and look at the conditions under which we boil a substance. For instance, when I boil water or boil any substance, liquid, I go across like that by keeping the pressure fixed and changing it, and then at a certain temperature it boils. When you boil a beaker of water on a stove in 1 atmosphere pressure, the pressure is the same in both phases, the temperature is the same at the boiling point in both phases. So we have a system where the temperature and pressure do not change across the phase, and we need to know now what is it that is the same, what kind of energy is the same in both cases. Well, remember that the internal energy was a function of the entropy of the system, the volume of the system, and the number of particles. So for a fixed amount of substance, which is what we are looking at all the time, this thing is not there, it is fixed. it is a function of the entropy and the volume, and we indeed saw that du was equal to Tds minus Pdv. But now I would like to be able to control the temperature and the pressure, those are my control parameters if you like, and I would like to maintain those at fixed for both the phases across the phase transition. So I need to go from this thermodynamic potential if you like to another energy whose differential will have a dt here and a dp here, so that I can put those two quantities to 0. Well, how would I go and do that? If I took u and subtracted Ts from it, then it is clear that if I take the derivative here du minus Tds minus sdt, you end up with minus sdt, this gets cancelled out. And similarly, to kill this I need to add a Pv here, then this Pdv gets cancelled out and is replaced plus by a plus Vdp. So if I call this G, it is the definition of an energy called G, the Gibbs free energy, implies that dG is minus sdt plus Vdp for a fixed amount of substance, and then you are saying that at constant T and constant P, when it is boiling, this and this are 0 because dt is 0 across the transition, dp is 0, therefore dg is 0. It is another way of saying that the Gibbs free energy per particle is the same in two phases when you are on a coexistence curve. That gives you the definition of this coexistence curve. So on every coexistence curve, the Gibbs free energy per particle of this phase and the other phase are the same. Ditto here on this side here. The Gibbs free energy per particle G over n is equal to the chemical potential. So the physical significance of the chemical potential is that it represents the Gibbs free energy per particle, and in a coexistence of two phases in the PT plane across a coexistence curve, the Gibbs free energy of the two phases are equal to each other. That is what determines the phase equilibrium, and that translated to the case of three phases gives you the triple point as well. So this is an extremely elementary introduction to the idea of a change of state, more precisely of a phase transition, and specifically we have looked at the phase transition of a liquid to a gas and vice versa, and introduced the idea of a critical point. So statistical mechanics starts at this point and goes on to understand the intricacies of this phenomenon called phase transition.